So far, we have defined the work done on an object. Now, we will define the energy, which is the topic of this chapter, and we will show the relation between the energy and the work. We first introduce the concept of kinetic energy. This kinetic energy is associated with the moving object. By definition, the kinetic energy of an object with mass m moving with the velocity v is defined as K, which stands for the kinetic energy, is equal to the half of the mv square. That is, if the object with mass m is moving with the velocity v, this v is the speed or is the magnitude of the velocity, and m is the mass of the object. Okay. We can show that this kinetic energy is closely related to the work done on an object. In fact, we have that when work is done on a system and the only change in the system is in its speed, the only change in it is the speed, the net work done on the system equals to the change in kinetic energy of the system. It means that if we look at this figure, we have an object with mass m. Okay, and if there is a net force, summation of F here, exert on this mass m, and this mass m moves. Since this mass m is moving under the net force, it has the acceleration. And the acceleration makes the velocity change from vi to vf. If we calculate the work done by this net force F to be W, okay, this is the work done by the net force. Maybe we can say that it's the work done from the applied force, which equal to the net force, the integral of net force dot dr from the Ri to Rf, and we will show that this will equal to the change of the kinetic energy, which equal to the half of mvf square minus half of the mvi square. So the work done by the applied force for the net force will equal to the change of the kinetic energy, and we call this the work kinetic energy theorem. The work kinetic energy theorem. Now we will prove this theorem. Now this is the proof. Consider an object of mass m. An object of mass m and this object is subject to the force F, so it will move with an acceleration, and we must have that this F is equal to the ma. A is the acceleration of the object, which is equal to the m dv by dt. This comes directly from the definition that the acceleration is equal to the rate of change of the velocity. And if we let the object move in a short time interval, okay, if the object moves in a short time interval, and if at the initial point here the object moves with the velocity v, and after a short time interval the object moves to the new position here, and this is the displacement r, and we can approximately that r is approximately equal to the t, the v times delta t. This approximately is valid when delta t is small, because if the delta t is small, we can assume that the velocity of the object change a little bit, maybe very little, and we can approximately assume that the displacement is equal to the initial velocity times the time interval dt, delta t. Okay. If we want to calculate the work done during this time interval, we want to calculate the work done during this time interval, we can have that W, delta W, which is the time of the force F during the time interval delta T here, is approximately equal to the F dot delta R. Okay, this follow the definition of the work. And when we substitute the force F and the displacement, okay, so we have that this is approximately equal to the m dv by dt dot v time delta t. Okay. This equation is in the form of differential equation, and we may cancel this dt and delta t. As I mentioned before, we use the symbol dt, but it is nothing. It is just the delta t when the delta t is very small, right? The dt is the delta t when the delta t is very small. So in this case, we can write this term as m delta v over delta t, with the condition that delta t is very small, or we use the notation that delta t is approach 0. So these two terms may be cancelled. This is not exactly, because if you go to the math textbook, there is a process. It's called the chain rule, that how to cancel these dt and delta t, but at the end it cancels. So I will not go into the detail of mathematics, but it's like an algebra that you can cancel delta t here and delta t here. But keep in mind that this valid only when delta t is very small. So at the end we have that this is equal to the m v dot dv. Okay, which equal to m times vx times dvx plus vy times dvy plus vc times dvc. Okay, this comes from the property of the dot product that we have discussed before. So this is the work done on the short time interval. Okay, if we want to calculate the total work, it can be done using the concept of the integral. So the total work is equal to the summation of the delta W, which we can say that it is equal to the integral from the initial position to the final position of f dot dr. Okay, but now we express this delta W in terms of the velocity. So we have to change the variable a little bit to be the velocity to make the integral easier